Hello everyone, I am MD Rafiqul Islam Robin, a fourth year computer science PhD student at the University of Houston. Now I will present our paper on the generalizability of neural program models with respect to semantic preserving program transformation. In this paper, we propose a model agnostic approach to evaluate the performance of neural program models on unseen data. This was a joint work among researchers from University of Houston, Singapore Management University, Visa Research and the Open University. Deep learning has increasingly been used for various code intelligence tasks, such as code summarization, which is popularly known as method name prediction. In this task, a trained neural program model, given the body of a method as input, aims to predict the name of that method. While the performance of such neural program models for intelligent code analysis continues to improve, our understanding of how reliable these models on unseen data is largely unknown. For example, a neural program model such as code-to-vec, given this code snippet, can correctly predict the target method name as compared to. But a simple variable renaming from other to var0 can change the prediction from compared to get count. Therefore, the question is, are these models generalizable or robust to unseen data beyond the data it has been trained or tested? To investigate this question, in this paper, we introduce the semantic preserving program transformation technique to evaluate the generalizability of models. Our approach relies on a metamorphic relation. The output of a neural program model should not differ on semantically equivalent programs. To this end, the evaluation approach is divided into two main steps. First, generating new semantic preserving programs and then comparing the output with original program. We apply 6 semantic preserving program transformation: variable renaming, loop exchange, switch to if, boolean exchange, permute statement, and unused statement. We apply transformation on original program and then generate semantic preserving transform program. Then we compare the output of models between original program and transform program. Any change between the prediction of model is considered as misprediction. We compute the overall prediction change percentage and define that as the criteria for model's generalizability. Therefore, in our evaluation, the lower the prediction change percentage on transformed data, the better the model's generalizability. These are the examples of each semantic preserving transformation. The variable renaming renames the name of a variable. The loop exchange replaces for loops with while loops. The switch to if replaces a switch statement with an equivalent if-else statement. The Boolean exchange changes the value of a Boolean variable and propagate this change in the program to ensure the semantic equivalence. The permute statement swaps two independent statements in the program. And the date code insert an unused statement in program. Moreover, a program may have multiple places to apply transformation. For example, the following program counts the presence of the target in an array. It has 4 variables. We can either rename a single variable at a time, or we can rename all of them. Even we can randomly select X% of variables and then rename them. By applying this different transformation technique on different places in program, we have created various semantic transfer programs. We will use this generated transfer program as a proxy of unseen data for evaluating models prediction. In this paper, we evaluate the generalizability of 3 popular models, code-to-vec, code-to-seq, and GGNN, across 3 Java datasets for method name prediction tasks. The code-to-vec uses the path between leaf nodes in abstract syntax tree to represent a program. Code2Sec also use AST of program but split token into subtoken and use LSTM for sequence prediction. On the other hand, GGNN use data and control flow from program. These 3 different models use 3 different program representation techniques. This table shows the prediction change percentage for Java large dataset. We found that the models are vulnerable to semantic preserving adversarial transformation. Every small change in program can alter their prediction in some degrees. For example, Simply permuting two independent statements can cause more than 60% misprediction for code-to-back. In most cases, the effect is much higher for code-to-back and less for GGNN. The result shows that the GGNN model that use data and control flow seems more robust than code-to-back and code-to-sec that use the AST of program. We also observed the similar result for Java Mid and Java Small dataset. We next compute the change of prediction with respect to the length of method. The code-to-back shows a notable increase in prediction change percentage as the length of method grows. Code-to-sec also shows similar trend, but GGNN seems to be more stable to the length of method compared to code-to-back and code-to-sec. We see that the larger program in code-to-back models are more vulnerable to transformation. We also check the change of prediction with respect to dataset size. For code-to-back and code-to-sec, in most transformation, we observe that the effect of prediction change is reduced as the dataset size increase. Thus highlight that the models when trained with a larger dataset may be more stable than when it trained with a smaller dataset. However, we do not observe such pattern for GGN. To investigate when the transformation is more powerful, we also differentiate the method based on their actual correct prediction and incorrect prediction by models. Comparing the correctly predicted method with the incorrectly predicted method, we can see that the change in prediction happens more frequently in the originally incorrect method for all models. We also see that GGNN is more stable in the originally correct method. Therefore, it has very low prediction change for originally corrected method compared to code-to-back and code-to-sec. Moreover, there can be multiple places to apply transformation in a program, and therefore we evaluate both single place and all place transformation. If we check the distance between single place and all place transformation, the gap is more than 10% for code-to-back and code-to-sec. But for GGNN, the gap is very close. Even for some cases, the all place transformation has a smaller prediction change percentage value than the single place transformation. While all place transformations are more likely to induce more prediction in code-to-back and code-to-sec, the performance of GGNN remain relatively similar under both types of transformation. Apart from single place transformation and all place transformation, we also apply X% transformation, where we randomly pick X% place from a program and apply transformation on that places. The result shows significant change for variable renaming transformation. The performance of GGNN in terms of prediction change percentage remains similar in all cases under X% transformation, but the prediction change percentage of code-to-back and code-to-sec increase as the percentage of transformation increase. These are the key observations from our experiment. We found that neural program models are not often generalizable or robust to unseen data. A very small semantic change can alter their prediction. Larger programs, smaller dataset, and originally incorrect methods are highly vulnerable to semantic transformation. Multiple transformation, such as all-place transformation and X% transformation, are more likely to increase misprediction. And in almost all cases, we observe that the data and control flow-based models, such as GGNN, is more stable than AST-based models like code-to-back and code-to-sec. We first introduced our approach as a black box testing framework in 2019 at ASA late-breaking results track. After that, we found other researchers are also investigating the generalizability and robustness issue of neural program models from various aspects. In summary, in this paper, we propose a semantic-preserving program transformation technique to evaluate the generalizability of models on unseen data by generating new transformed programs. Our evaluation on 3 models and 3 datasets for method and prediction tasks show that the models are vulnerable to small semantic change. However, the data and control flow-based model, such as GGNN, are more stable than the AST-based model, like code-to-back and code-to-sec. Thank you.